This is a famous equation. It describes the natural phenomenon of cooling bodies sitting in an environment that is at a lesser temperature than itself. Now, the interesting thing in this equation is the negative sign here. What this means is that the temperature of the body always head towards the temperature of the environment. And how so? Let's say T, the temperature of the body, is greater than the temperature of its surrounding. Now, if T is greater than T of environment, this whole thing is positive. And if this is positive, positive times a negative sign makes this whole thing negative. So the change is negative in a negative direction. So this means that the temperature will decrease. So the decision is that if T is greater than TE, the temperature of the body decreases. Now let's see what will happen if T is less than the environmental temperature. In this case, as T is less than temperature of the environment, this thing is a negative, as this is larger. If this is a negative times a negative means this thing will be positive. Now, as this is positive, T will increase. So, if T is less than the temperature of the environment, T will increase. So, it means that whether T be less than the temperature of the environment, whether T be more than the temperature of the environment, it does not matter. It will always head towards the temperature of the environment. If the environmental temperature is less, it will decrease. If the environmental temperature is higher, it will increase. But it will always head towards the temperature of the environment. Now another example is similar to this one, as it was given by the same scientist, Newton himself. That example is Newton's laws of motion considering constant gravity. So if a falling body, if we want to describe the motion of a falling body that is experiencing a constant gravity, then the equation describing it will be something like this: d square y by d t2 will be equal to negative of the gravity. Now y here describes the distance of the body from the surface of the earth, and t is the time that we are calculating against, and g is the gravitational acceleration force towards the center of the earth. So this negative sign again tells us that the acceleration of y will be towards the surface. Now we need to understand why, even if this is the surface and we dig a hole in the surface and we drop a body from here, why not it go here? Couldn't it just come to a balance at the surface? This is what this is showing. It is showing that the acceleration should be always towards the surface. But actually what happens is that when we dig a hole, the surface has gone here, gone below. That's why this falls down. The surface is not here anymore. And then the distance from the surface has to be calculated like y here and the depth of the hole itself. That's what the distance of the body will be from the surface. Now let's take a more generalized look at what Newton's laws of motion tell us. Let's say there is a falling body, but it is of a significant distance from the center of the earth, so that we don't need to model the equation from the surface of the earth. We can actually take the actual radius from the center of the earth. Let's say this is the earth, this is the center, and this is a body away from the center. This is its distance. Now, for simplicity, I am not using the vector of r, even though I know that this is a vector. And for simplicity, I am just omitting the vector part. Let's just say the distance. Now, the equation describing the motion of this body. This is the body. The equation describing the motion of this body is something like d2r by dt2 is equal to gravitational constant times the mass of the earth divided by r square. And we know from our previous knowledge that this is equal to the gravitational acceleration. We studied this in our intermediate course. Now, you might think that such differential equations are only useful in describing situations of such massive proportions, but it's not so. Even in very simple systems around our daily lives, differential equations are needed to describe the characteristic of a system, because simple harmonic oscillations can only be modeled by using a differential equation. How? We know about Hooke's law, and Hooke's law applies to springs connected to bodies. So let's draw a spring, and there is a body of mass m connected to it. Let's say this is the equilibrium position of the spring, and the mass is displaced to a distance of x from the equilibrium. Now that we have pulled it away, the spring will try to go back to its equilibrium position. And what will be the equation that describes the motion of this body now, depending on the spring? The equation that describes it will be m times x double dot will be negatively related to k times x. So what this means is that the force experienced by this body will be equal to negative of the spring constant times the distance that it was displaced. Why this is negative and why it is dependent on x? Firstly, it is dependent on x because as we pull the body away from the further and further away from the equilibrium, the force exerted by the spring gets larger and larger until it reaches its limit, and then that is the point where the spring gives. But we are not considering the phenomenon where we pull the body away from the spring so much that the spring loses its integrity. If we are considering it to a moderate level, then we see that as the body is pulled further and further away, the force exerted on it by the spring increases. So we can say that the value of force applied by the spring on the body increases or decreases with a linear linear what can I say, a linear relation to the distance from the equilibrium. And now let's take a look at why there is a negative sign here. Why? Because we see that if we pull the body this way, the force applied on the body by the spring acts this way. And if we depress the spring, if we push the body this way, the force applied by the spring will be this way. So it comes to us that the acceleration of the body due to the spring will always be on the opposite side, will be negative of the way we displace the body. So the acceleration will always be towards the equilibrium. If we displace it this way, it goes towards the equilibrium. If we displace it this way, it goes towards the equilibrium. So the acceleration will always be towards the equilibrium of the spring. Now let's take a look at a damped harmonic oscillation. The first example of oscillation that we took a look at was that there was no dampening force. Now let's say, consider if there is a spring here, a body connected to the spring, and this body is sitting on a surface that has a friction. So there is a friction here. The mass of the body is m and the spring constant is k. So now the force exerted, so the force felt by the body, it is mx double dot. This is the force felt by the body. The body doesn't know who is contributing to the overall force. It just feels the overall force. So this is the overall force felt by the body. Now who are contributing to this force? First, the spring is applying a force, and then the friction is applying a force. Now this friction force is dependent on the velocity. That's why there is a dot here. This is the equation that describes a damped harmonic oscillation. Now if we take into consideration that there might be an external force again applied to this. Let's say there's an external force, let's say F, and for just to generalize, we take F as a function of time, because we do not know if F is a constant or F depends on how the time progresses. So let's just say F is a function of time. So in this case, when there is an external force, the equation will be this plus F of t. Now you might ask why we have taken negative here, and we are not taking negative here. We have taken negative here because we already know that the forces acting on the body will be on the opposite side of the displacement. But as this force does not depend on displacement, rather it depends on time, this force will not, we are not able to conceptualize whether this is against the displacement or this is towards the displacement. That's why we are taking it as positive, because even taking this as positive makes us safe. If this force is a negative force, negative times positive becomes negative. So we are not in any danger. If this is a positive force, then positive times positive becomes positive. In the end, the positive sign does not change the overall sign of the time itself. But if we were to take a negative sign, it would change. So we have to take great caution when we are trying to put a negative sign in front of a term, or when we are building a differential equation. Because if we take the positive sign, we are safe. The positive sign won't affect the overall sign, but the negative sign does affect. So if we make a mistake in conceptualizing it somehow, then the whole equation will be wrong. Now that we have taken a look at some important and famous differential equations, let's take a look at how to solve these differential equations. We are going to learn our first method of solving a differential equation. It's a very basic method and it works on very basic equations. And the method is called separation of variables. Now, which equations do this method work? The equations that this can handle is that the equation that can be separated into two variables, and the terms containing the two variables can be taken on two sides of the equal sign. So what I mean is that if there is an equation, there are four terms, let's say this and this, this and this, and this has terms A, this has terms Y, this has terms X, Y, then somehow the equation can be rearranged so that all the terms containing Y are here and all the terms containing X are here, so that no term containing X is on this side, no term containing Y is on this side. All the terms that contain X, just X is here. All the terms that contain Y and only Y are here. And if an equation can be separated in this way, then that is the equation that we can apply the separation of variables on. Take. Now let's see an example of using the separation of variables technique. So I will say that this is example 1. Now the equation at hand is y prime is equal to x times y minus 1. So we can see that this is the only term that contains x. This term contains only y and a constant. We are not concerned about the constant, just y. And this term contains both a y and also x. How? Because this term actually is like dy dx. So this term actually contains both y and x. So we have to separate this. If we bring this term containing y over to this side and this term containing x over to that side, then we get dy over y minus 1 is x times dx. Now you just need to integrate this and we will get a solution. So what is the result of the integration on this side? The result will be ln, the absolute value of y minus 1, will be equal to x squared over 2 plus a constant. Now, why are we taking the absolute value of y minus 1 and not this? Why not this and this? Why this? This is because, as you know, this is the natural logarithm of the value y minus 1. But we are not sure whether y is greater than 1 or less than 1. If in some case y is equal to 1 or less than 1, this will not work. Because the natural logarithm or any kind of function for that matter is defined for only positive, any kind of logarithmic function for that matter is defined for only positive values. It does not work on negative values. So we have to ensure that this value is positive, and the only way to do that is taking the absolute value of this. We cannot take this and expect that magically it will ensure itself. We have to do it ourselves. We have to take this. Now, I will keep the original equation here and underline. So this eventually comes here, and on the next line we can do e to the power x squared over 2 plus c. Now, as this is an absolute value, y minus 1 will be equal to plus or minus e to the power c times e to the power x squared over 2. And so, if we consider all of this, we see that this is actually a constant. So let's just say this is C1. So let's take capital C as our overall constant, and the solution will be something like 1 plus a constant times e to the power squared over 2.